Hi everybody, today I will present the importance of the secure coding. My name is Bassem Taamallah and I work in HID Global as Principal Firmware Engineer. So we will start with a small presentation of our company, HID Global, small presentation of our team, and we will focus on the importance of the secure code development. So HID Global is created in 1991 as a provider of security access solution, and starting from 2000 it was acquired by ASA Abloy. In HID we provide a big range of product for credential like COS, iClass, and also a big range of reader technology. And for in this different product like the reader technology, there is always different different module which are used or shared between the model. For this our team is coming in the game. Our team is called Core Firmware, and in our team we are providing a wide range of module in the top of our hardware development platform is like WFI, NFC, BLE, and we have also module for UWB, and also different firmware module around the secure element for file system management and also for the crypto kernel. And our goal in our team is, by providing this firmware module, is to try to reduce the time to market and the cost of our product by coming to the market very quickly with the most effective product. Try to offer a modularity that we can integrate our module as easy as possible. Try to adhere to the industry standard, and also we try always to work on the latest technology to ensure that the product it will use and reused in different product. And also the last thing and not the least is we always offer a secure and robust module. And speaking about the security that we are offering in our module, here I would like to dig in the secure code development that we are doing in our team. So first of all, let's start why we need secure coding in first place. So because we can do development and we have something functional, so why we need to have this secure coding? First of all, the secure coding, it will help us to ensure that the secret information or the secret access still secret. We need also to ensure that a person or an entity who didn't has any authorized access should not access to any sensitive data or any sensitive asset. And we need also to prevent that non-authorized action can be done by, for example, skipping a mechanism of security based on cryptographic operation. And also prevent that anyone can inject a malicious code. This malicious code, it will have the impact that it will change the behavior of the chip. And also the most important thing that we need also compliant with certain operating regulation, because now the security is not nice to have, is also mandatory. And when we are speaking about this malicious code and this non-authorized access, this is what we call attacks. And attacks can happen in several parts of if we take here the example of a physical access control, it can happen, for example, in the card or in the smart or in the application or in your smartphone. So it can be attacked, and also it can be attacked even in the reader side, and it would be more catastrophic because a reader usually it can allow you to get access to the facility. Although sometimes it's easier to get a card or smart card attacked because it's always distributed and in the hand of everyone. The reader is more difficult because reader usually is hanged somewhere in the front of a building, but it's always more catastrophic when we can bypass the reader. And the attacks, we can, we can regroup them in two big type of attack. There is the side channel attack and also the fault injection attack. The side channel attack is by monitoring the activity of the chip, and we can figure out some some sensitive data, or maybe the activity of the chip by, for example, checking the power consumption, checking the electromagnetic radiation, or even the time which is for computing for certain operation. It will leak some data or give you an idea what's happening on the chip. And this is what we call the non-invasive attacks, because we just monitoring what's happening in the chip. The second part is the fault injection, which is we try to bring the chip in a kind of unstable behavior, and this unstable behavior, it will leak some information, or it will leak some data which is really important. And there is different type of fault injection. We can try to, for example, focus a laser beam, and with that we can flip some bits, or do, for example, make some glitch in the power or glitch in the clock to lead the chip in some unstable behavior. Let's start with the fault attacks. So the fault attacks, as I said in the previous slide, that we will try to bring the chip in kind of unstable behavior, and by injecting some fault. And with this kind of injection of fault, it will make the chip or the program in general skipping certain operation, which is some security setting or some cryptographic setting. Like, for example, when we are by focusing a laser beam in a certain part of the chip, we can do a bit flip in the memory, and by making a bit flip, we can change a decision. For example, we can skip the whole authentication process or the MAC calculation to check if the data is correct. And what we can do also, that we can with this type of attack, we can force a buffer overflow, for example, in case of sending data. So we can send data more than we need it, and the data usually is stored in the RAM, and it can be by bad luck that in this RAM we have some sensitive data like keys, which should not be in usually, but when we are sending more data, so we can leak the key. And this is what we call here dumping the memory. Or we can even do the opposite by just blocking the sending of a lot of data, or just blocking the key loading, for example, and with that we will have a key which is not loaded for an encryption operation. Let's look to a more concrete example, because here by showing what type of this attack it will do, and how we can also prevent this with the security coding. And from here, I would like to emphasize about the security coding. So here, for example, we have a function to just allow access by unlocking a door, or just sending an error message that you cannot access. And the decision it was based in this variable. For example, here is pin correct, which is a Boolean, and Boolean in C language can be 0 or 1. And just by flipping one bit, we can change completely this decision from sending an error message to unlock the door. So what we can do, there is a lot of security pattern that we can apply, and here I try to show you one of this pattern that we can apply. For example, when we are speaking about this Boolean, we should not use the simple Boolean type, but we need to use a longer type with the maximum of Hamming weight distance, and with that, it's really difficult just by flipping one bit to change the decision. What we can do also is here that we have, in our case here, we have secure false and secure true. And we need also to check if there is an invalid value. And if it's an invalid value, we need always to lead the processing to what we call a security reset or a trap. This is one of the patterns that we can apply in case of to really check that we cannot change the decision or skip a certain part of the code. There is another typical example when, for example, we are trying to loading a key, and we would like that instead of loading this key, we just block this loading and we load a 0 value, because when we are doing an AS operation with a 0 value, it is kind of known value, and then we can figure out the text and the plain text because the key is very known, is a null value. And with that, we can use a mechanism, what we call redundancy, just by, instead of using one counter, we will use double counter. We are going in two opposite direction. And we're checking for each step that these two counter are still correct. And if they are not correct, we should try to force the chip to make a trap, or what we call again security reset. So here again, so how it's really important to apply all this mechanism of security when we are coding. There is also some other pattern that we can apply, but in general there is a lot of good practice. I try to pick some of them. So for example, we should not use simple value like this secure false and the secure true. We need always to use bigger value with the maximum Hamming distance. In case of communication buffer, we should avoid using an intermediate buffer, which is in the memory, and that can leak also data in case of buffer overflow. And we should always, when we are making some processing which involving some crypto operation, we need always to clean the variable. We need also to flash the cache if our system containing an internal cache. What we can do, we need always to protect our data by applying a mechanism of CRC, or if we have just simple variable, we need always to make a redundancy with an inverted value for our variable. Also, to avoid skipping certain part of our code, we can apply what we call flow protection by adding, for example, a magic number which is updated in the beginning of each function, and in the end of the process we check the content. And also for the Stack Overflow, there is the mechanism of adding watermark in the end, and this watermark, it will be checked each time, and with that we be sure that the stack is still in the limit. This is, let's say, some good practice to prevent false attack, but as I say, there is really a lot of other mechanisms that we can apply, but here always it depends from your implementation and what you want to protect exactly. Let's move on to the second type of attacks, what we call the side channel attacks, which are the most difficult, because here there is not really an intervention, or we don't force anything in the chip. Just we will monitor the activity of the chip, and there is different type of side channel attack. There is what we call the timing attack, is just to measure the time which is needed for a certain processing, and with that we can figure out what the chip is doing, and based on the data which is used, we can figure out what the chip is doing, and then we can have an idea about the sensitive data which is manipulated. There is also the power management attacks, and the power management attack is to monitor the power of or the consumption of the chip, and for here, for example, in this example, we have only an oscilloscope, and with monitoring the profile of the power consumption, we can figure out what's going on the chip. And for the power consumption, there is what we call the simple power analysis on the differential power analysis, which is more sophisticated. There is also the communication response analysis by analyzing the response that we got from the chip, and based on that we can get an idea what's happening. And also the last thing, it's also like the power management is the heating management. So it's more, let's say, it's not really obvious, but when the chip is computing, is consuming power, and the heating, it will rise. So yeah, so let's take an example of the simple power analysis, or let's say the power attack. So here I take a code which is doing an RSA operation, RSA decryption operation. For the RSA decryption operation, we need to protect the private key. But we know when we are doing a decryption for the RSA, we are using an operation which is the exponentiation, and the exponentiation in some of the poor C implementation, it's based on the square and the multiply algorithm. So in this example, when we are using the private key, and we will take bit per bit. When the bit is 0, we just need to make a square operation. When the bit is 1, we have an extra operation, which is the multiply operation. So here we have an idea somehow that when the bit is 0 is only 1 processing. When the bit is 1, there is 2 processing. And by monitoring the power profile, which is here in this picture, we can see if we have 2 power peak, it's 1 bit because we have 2 computation. When it's only one peak, which means here also it's 1. But if it's one operation, we have only 1 power peak, so which means that it's this 0. And if we continue with that, actually the private key is leaked just by monitoring the power profile of the consumption. So there is also more sophisticated attacks, which is based on the differential power analysis. But for this case, I just want to show you how we can leak data just by monitoring the power consumption. There is also what we call the timing analysis. The timing analysis is just to check how the time which is spending for certain operation, and based on that we can figure out what the chip is doing. And here in this example, we want to check if the pin which is sent is correct or not. And if it's correct, the program, it will be spend more time, because we will check the first byte is correct, the second byte is correct, and the third byte is correct, so we'll spend more time. But if the pin is incorrect, so let's say the first byte from the pin is incorrect, we will spend less time. And with that, by measuring the time which is spent in this loop, we can figure out with several trial which pin is correct and which is not correct. And here, so I want to show through applying some security pattern during our development how we can prevent this. And the most technical which is used in this case is we need to apply what we call the time invariant implementation. So, and globally in this timing invariant implementation, we need to make the process the same if it's the pin is correct or incorrect. And with that, it's really difficult to figure out what's happening. So in general, with the side channel they are more sophisticated attack, and also it's really one of the difficult attack to prevent. But there is some pattern that we can apply, and we must apply always. So the pattern is here. I didn't also put all of them, but the most important one is masking. What I mean by masking, for example, we need to hide always the key with a mask, which means that we need to, instead of processing the key, we need to process a masking key. And after we finish the process, so here we can remove this mask. And this mask also, it need to be generated randomly, and it need to be generated for each process, for each process. And with that, we guarantee that the key itself, it never been in plain and never processed as it is. And there is also another technique which is called the hiding, and the hiding is to try to make some dummy operation. We try to make the power consumption random. There is some software mechanism, and also there is some hardware mechanism for that. And by making the operation random, the power consumption, we cannot really figure out exactly what's happening. We can, if we take an AS calculation, we can try to inject some dummy operation, and with that, we cannot really figure out which is the dummy operation and which is the correct operation with the AS. So yeah, so here, as I said, there is always a lot of pattern that we can apply, and these two the most famous of them, and yeah, but there is always some other. And again, it's really important to understand what we want to protect, and which type of attack we need to prevent. So that's why. So the secure coding is not just applying some pattern as I showed in the previous slide, but we need to think the secure coding from the beginning. This is what we call the security by design. And we should not leave the security until the end, that we got something functional and now we will think about how we can adding some security mechanism. It should be something in the process from the beginning, from the design of our product or our module. We should think about it. And also we need to avoid something what we call security by obscurity, which means here, for example, I put this picture here in the case of Death Star in Star Wars. So just we put the kernel in kind of really inside, and there is a maze to get to it. But if someone have the map of this maze, it's really easy to destroy it. And this is the case in the movie. And also some other important thing, that when we have a code functional, the corner case should be tested, because the corner case is the point where a hacker or attacks can be exploited. And also one last thing, we have always some security mechanism based on some software pattern, but we need also to use the hardware countermeasure, because nowadays all the secure element or even a general purpose controller, they have a security mechanism, hardware security mechanism that can be used. And for example, each secure element, they have some hardware countermeasure that can be used. And if we are using, for example, a controller based on ARM architecture, there is the NPU, we can use the ARM trust zone. And also we need to use when we are trying some random stuff, we need always to use the true random number generator, which is provided by the majority of the controller vendor. There is the timer watchdog. So, and all this to show you how really important to have all this security measurement. So, in the end, what I want to tell, that security attack is not kind of attack that we know them and it's okay. They are constantly evolving, and we need always to adapt our code, and we need always to invent a new secure pattern to protect against the new attacks. And we need always to keep an eye what's happening, and also try to update our code based on the threat that can happen. Yeah, so that's all from my side. And if you are interested to what we are doing related to security, you can join Shaiti in Graz. Thank you very much.